Alright, here we go with our last iChem for the semester on KW, pH, and pOH. These are all calculations that we use to talk about the concentration and the degree of acidity in solution. So first of all, what is this KW that we're talking about? Well, when you think about water kind of exists. It's an ionic compound and a covalent compound at the same time. So it's in a balance between hydrogen and hydronium ions. So this KW value really tells you about the ratio between these. Always, always, always for water, the two concentrations, this is somewhere later in your notes, but you kind of need to know now, the brackets mean concentration. Whoops. Concentration. And the units of molarity. So, the concentration of hydronium ion, which remember is the same as the hydrogen ion, we use these interchangeably, times the concentration of the hydroxide ion always equals 1 times 10 to the negative 4. That means that if you know one concentration, you can easily find the other by applying this equation. We can also look at the two concentrations and compare them to decide if it's an acid or a base. So we know that acids produce hydronium or hydrogen ion when they're dissolved in water, which means they'll shift the balance and there'll be more hydrogen ions or hydronium ions than hydroxide ions. And for a base, it'll be the opposite. The bases produce hydroxide, so it shifts the balance. Hydroxide concentration goes up. So to keep this constant, hydronium ion concentration goes down, and OH is greater than H for a base. So real quick, let's do a couple calculations applying this. If you know one concentration, you can find the other. So here's the hint. If the problem involves OH and H3O, hydronium ions, then you use KW equation to solve for the other one. Okay, so remember KW is H3O times OH gives you 1 times 10 to the negative 4. So let's plug in what we know. In place of hydronium ion, we can put 3.98 times 10 to negative 13. And then OH concentration is what I'm trying to find. So I'll leave that in there. And as always, always equal to 1, times 10 to the negative 14. So to solve for OH, I need to divide both sides by this. It's a good idea to keep it in parentheses so that you're telling your calculator to do the right thing here. Remember when we use these big numbers in scientific notation, especially if you don't have that EE button on your calculator, it's a good thing to put parentheses. Remember, we can replace times 10 to the with the capital E on our calculator. If I plug this in, 1.0 times 10 to the negative 14 divided by 3.98 times 10 to the negative 13th, I get an OH concentration of 0.25 molar. All of these, remember, have units of molarity. So now I need to compare these. OH is 0.025. H, or hydronium, is 3.98 times 10 to the negative 13th. That means I would move this decimal point 13 spots to the left. That'd be a really, really, really small number. So OH is greater than hydronium. Hydroxide is greater than hydronium, so that means this is a base. Let's do one more like this. So now we want to know what's the concentration of hydronium ions in wheat flour in water solution if the hydroxide ion concentration is 1 times 10 to the negative 8 molar. And and then decide acid, base, or neutral. So same thing, apply the KW formula. Whenever you know one concentration and you want the other, set it equal to 1 times 10 to the negative 14. So hydronium is what I'm trying to find, so I'm leaving that in as a variable. Times OH, hydroxide, which I'm given, 1 times 10 to the negative 8. And this is equal to 1 times 10 to the negative 14. To solve for hydronium, divide both sides by this. Keep it in parentheses, especially if you don't have that E button on your calculator, to avoid the order of operations mistakes. Over here, this cancels, and I have 1.0 times 10 to the negative 14 divided by 1.0 times 10 to the negative 8. My hydronium ion concentration here ends up being 1 times 10 to the negative 6. So I want to compare these numbers. Times 10 to the negative 6. I'm just going to look at these out of scientific notation. So I'm going to take the decimal place, which is after the 1, and move it to the left 6 places. That means I point 0, 1, 2, 3, 4, 5 zeros, and then a 1. I move this 6 spots over. I'm going 1, 2, 3, 4, 5, 6. Whereas my hydroxide ion concentration is 1 times 10 to the negative 8. From the decimal point, move over 8 spots. That's 1, this, 7 zeros. So many zeros I'm losing count. So the more zeros in front of the number, the smaller the number. So hydronium ion concentration is greater than hydroxide ion concentration. So this is, by definition, an acid. There's actually a more useful way to decide acid or base, and that comes from using the pH scale. So pH measures how acidic or basic a substance is. The scale ranges from 0 to 14. A pH of 7 is considered neutral, not an acid, not a base, neutral. Water, with nothing mixed into it, has a pH of 7, completely neutral. What it means also is that the concentration of hydronium ion and hydroxide ion is equal. pH of less than 7 is acidic. What that means is you have more. Same thing with our other definition. A pH less than 7 indicates that hydronium ion concentration is greater than hydroxide ion concentration. And a pH greater than 7 is basic and indicates hydroxide ion concentration is greater than hydronium ion concentration. So 7 is neutral, less than 7 acid, greater than 7 it's a base. So what does the scale mean? Well, pH scale is what's called logarithmic. So what it means is a whole pH value increase. So from 0 to 1, you see it makes it 10 times smaller in concentration. 10 times smaller, every whole number increase in pH value decreases the concentration by a factor of 10. So 1 increase in pH is essentially moving the decimal place over 1 more place to the left. You can look at it in concentration with zeros, or in scientific notation. That move to the left of the decimal point is represented by negative exponent here. So the bigger the negative exponent, the higher the pH. So put this in other words, the higher the pH, the lower the hydrogen ion concentration. That feeds back into what we just said. The higher the pH, greater pH, hydrogen ion, hydronium ion concentration is less than hydroxide. So again, the higher the pH, the lower the hydrogen ion concentration, or hydronium ion. Remember, they're the same thing. So we can use pH as a simpler measure of whether it's an acid or a base. Remember that that bracket means concentration in units of molarity. And then also remember, if we know one concentration, we can find the other using the Kw equation. So the Kw still comes into play here sometimes. Notice these two equations are the same thing. pH is the negative log of the hydrogen concentration or the negative log of hydronium ion concentration, because this is the same as this. Some problems will give you the H or hydronium concentration, and then you can plug just directly in. Other problems will give you it indirectly via the hydroxide ion concentration. Then you need to use Kw and then plug it in. So let's do an example. Analysis of a sample of maple syrup reveals its concentration of, now this is hydroxide ions, is 5.0 times 10 to the negative 8. I want to know the pH. pH is equal to negative log of the hydrogen or hydronium ion concentration. I'm given hydroxide. I have this and I want this, that's Kw. So hydronium ion concentration is what I'm looking for, times hydroxide ion concentration, which I'm given, is equal to Kw, which is always 1.0 times 10 to the negative 14. So divide both sides by 5.0 times 10 to the negative 8. I get H3. Hydronium ion concentration is equal to 2 times 10 to the negative 7. Now this is what goes in to here. So pH is equal to the negative log 2 times 10 to the negative 7. You probably remember definitions of logs and are hopefully familiar with how to use them in your calculator from advanced algebra, but this is a log base 10, so it's just a log button on your calculator because it, remember, 10 times change every time. So on my calculator, I would just put in the negative sign, find the log button, and then plug in 2 times 10 to the negative 7. I get 6.70 is my pH. pH has no units. Let's do one more. Okay, so I have a sample, bananas and water, and I have the hydronium ion concentration this time. pH, remember, is the negative log of the hydronium ion concentration. If I'm given this in the problem statement, this becomes a really easy question, because all I need to do is do negative log and plug in that number, 2.51 times 10 to the negative 5th. So negative sign, log button, 2 times 10 to the negative 5th gives me a pH of 4.6. Notice that the pH is always within a whole number value to the exponent. It is here and it was here. That should be every time. Okay, so we can find pH given our different concentrations. There's another measure that's called pOH, which you would do the same kind of thing with the hydroxide ion concentration. And also note that pH plus pOH equals 14. We will pick up from this point on Monday, so don't necessarily worry about this part right now. Leave that place in the bottom of your notes blank, because we're going to make a map so that you can easily do any calculation in this whole realm of acids and bases. So don't forget to do the Google form, go back, get anything you missed in the notes. Be thorough, please.